Welcome, I am Eki Lagundi, and today we are diving into a high stakes global supply chain optimization. So, our mission is to manage a network involving five production sources: the US, Germany, Japan, Brazil, and India. So, these plants must serve five major regional demands across North America, South America, Europe, Japan, and of course, Asia. So, this is a multi dimensional puzzle. So, we have to account for fixed capacities, varying production costs in local currencies, and the volatile nature of international exchange rates. So, over the next 10 minutes, I will demonstrate how we used mathematical modeling to find the sweet spots between the absolute cost cutting and, of course, the strategic operational health. So every good model starts with a clear architecture. So on one side, we have our supply sources, the factories. So each has a hard physical limit or capacity measured in tons per year. And on the other side, we have our demand regions, so which require specific tonnages to keep their market supply. So like the 270 tons needed in North America, our job is to fill the shipment blocks in between. So every choice we make here has a ripple effect. So a shipment sent from the US to Asia isn't just a logistics cost, it is a production decision that uses up limited US capacity and potentially prevents us from serving a closer market like North America. So logistics is often a game of currency. So our production costs are born in local denominations. So we have marks in Germany, yens in Japan, and reals in Brazil. So to compare these fairly, our model converts every single cost into US dollars using current exchange rates. So notice the massive disparity. So Japan's production cost per ton is a highly competitive 1,674, while the US plant operates at 10,000 per ton. So without looking at anything else, the math tells us that Japan is our efficiency hero while the US is our high cost burden. So understanding these financial baselines is critical before we ever click solve. So in our first scenario, we asked the sulfur, so what is the absolute cheapest way to run this company? So we removed all constraints except for capacity and demand. So the result was a slash and burn efficiency. So because the US and Japan are high cost producers, the model completely shut them down. So it assigned to zero shipments to those plants, preferring to max out Germany and Brazil. So this gave us our lowest possible total system cost of approximately 7.42 million. So while the math is perfect, this scenario is a logistical ghost town. So it ignores the reality of keeping a global business actually running. So why can't we just leave those plants at zero? So in reality, a factory at 0% utilization is a disaster. So you lose your skilled labor, your machinery degrades, and you lose your foot in the door in that region. So this is where the minimum 50% run rate comes in. So this is a strategic constraint that forces every plant to operate at least half of its total capacity regardless of the cost. So it represents a pivot from short-term profit to long-term resilience. So we are essentially deciding that the cost of keeping these plants alive is a necessary insurance policy for our global supply chain. So to model this, we updated our constraints. So in scenario 2, the total outflow from each plant must be greater than or equal to 50% of its rated capacity. So now the US must produce at least 92.5 tons. So look at the shift in the data. So the US now ships 100 tons to North America because we forced the US to run. So the model had to take those tons away from a cheaper source like Germany. So this is a perfect example of a binding constraint. So the rule is actually dictating the flow of goods, overriding the natural preference of the lowest cost. So let's take a look at the price tag of our strategy. So by forcing that 50% utilization, our total system cost jumped from 7.42 million to 7.97 million. So that $550,000 difference is what we call the cost of readiness. So it is the premium SC consulting pays to keep its global footprint active. So as a student of management, it's vital to interpret this completely so it's not an error waste. So it is a conscious business decision. So we are trading $500,000 in efficiency for the security of having 5 operational hubs around the world. So this is the technical modeling, this is the setup. So our objective function is the total system cost cell set to minimize. So our decision variables are the shipment blocks. So we have 3 main constraint sets. So first is supply must not exceed capacity. Second is total shipments to each region must be equal to demand. And third is the sum of shipments from each source must be less than or equal to 50% by minimum run rate. So by using simplex LP engine, we ensure a global optimum. So this technical rigor ensures that our strategy isn't based on a hunch, but on a hard, verifiable data. So supply chains are dynamic, they are not static. So in scenario 3, we performed a sensitivity analysis. So what if we added 10 tons of capacity to Brazil? So Brazil is one of our star performers. Its production cost is relatively low at 7,306 per ton, and its transportation costs to South and North America are competitive. So by increasing its capacity, we are testing how much slack we can remove from the system. So if we give the model more of a cheap resource, it should theoretically lower our total cost even while maintaining the 50% rule for the expensive plants. The results of Brazil expansion are fascinating. So the model immediately utilized every single one of those 10 extra tons. So Brazil increased its shipments to North America to 20 tons. So by doing this, it allowed the model to back off from other more expensive shipping lanes. And even with the 50% minimum run rate still active for everyone else, the total system cost dropped to 7.79 million. So this proves that Brazil is a leverage point in our network. So investing in Brazil's growth is the most effective way to offset the high costs of our US and India operations. So let's summarize our data. So scenario 1 showed us the theoretical floor of our costs, but it was operationally impossible. And scenario 2, it gave us a realistic operating floor, but at a higher price. And scenario 3 showed us the path forward. So using targeted growth in efficient regions like Brazil to bring our costs back down towards the theoretical floor. So we have moved from a simple shipping problem to a strategic expansion plan. So this is the power of supply chain modeling. So it turns raw numbers into a clear roadmap for investment. So my final recommendation for SC consultation is twofold. So first, maintain the 50% minimum run rate across all the 5 global plants. The 550 cost of readiness is a sound of investment in global resilience. And second, prioritize the 10-ton capacity expansion in the Brazil plant immediately. So this move allows us to capture regional demand more cheaply, and it provides the best return on investment for the entire network. So by balancing these constraints, we ensure that our global supply chain is not just cheap, but sustainable and ready for whatever the global market throws at us next. So that is all. Thank you.